Good morning, class. I hope everyone's doing well today. Nice weather. Can't complain. As you noticed, I sent out the Blackboard announcement and the email for our next test. I will have an opportunity to do some review problems on Wednesday. Um, I know for some of you, you're always way ahead of the game, but I still think it's good just to have some opportunity to combine some ideas that we've talked about since the last test. And if I need to work on some other problems that I don't have time to get to, I'll do those. But I'll do some review examples. And just like last time, the testing window will be exactly the same. You will have the 2-day uh, window that will start on Thursday and end on Friday, just like we have done in the past. And you will turn in your test work um, with the Turnitin app on Blackboard, just like we've always done. So I appreciate your attention to that. It is important, and it is something that is part of the fabric, again, of the philosophy of the school, and of course, the standards of the school. So again, I appreciate your attention to that. I also sent out a Blackboard announcement about a signature assignment. The general education project, which is ongoing, basically in certain core courses offers a signature assignment, and this is going to be treated as a quiz grade. So you'll have an additional quiz grade, and the due date is on into the week after this. It is a problem that covers topics in chapter 7. And again, follow the directions. The basic idea is just to assess critical thinking skills, just like you do every day in a math class. So it's interesting that we have a signature assignment for math, because that's what you do every time you work a problem. And so just follow the directions. It's a very straightforward problem. And maybe some of the questions may seem a little bit untoward and not that relevant to you. But I could say this: imagine like you're teaching the problem to someone else, work through it, and then imagine that you're actually describing the technique to another student. So that might help you get into the right frame for that. But it'll be a problem you enjoy, and it's certainly very accessible. Now, today, of course, what we're covering will not be on the test. We've introduced the idea of the parametric representation for curves, and just the ideas that are involved there, how we actually treat a parameterized curve, and basically how we navigate the new type of notation. Again, when you, like I said before, when you get to Calculus 3 and you talk in more detail about curve theory, all of this will come back and be extremely helpful. Just remember that the calculus we introduce today will be the calculus for the Cartesian derivative. You will actually learn how to differentiate vector functions, which will be a different construct than what we're doing today. So with that said, let's go ahead and get into the mix with the calculus of the parametric equations. And I'll share my screen. The IPEVO software updated, so I think the actual display is improved. When it just did it last Thursday, right before a class, and I think it's an improvement. But I don't know. Maybe I'm seeing things that you all don't see. So when we talk about the calculus of parametric equations, what I mentioned last week is that maybe it would be good to have some way to recover the standard derivative, like the dy dx, the y prime of x, because we've got this parameter that we use to define the x coordinate and the y coordinate. And so is there a way to kind of backtrack and get to the Cartesian derivative that we are accustomed to in Calculus 1 and what we've been doing so far until now? So remember, for the parametric representation, and of course we'll make some assumptions about smooth, because we have to have fairly fairly good functions in order to do calculus. You know that. Um, Calculus is not applied to functions that have poor qualities, basically because it requires many characteristics that force the function to be, as they say, well behaved. So remember, I introduced the notation R of t. We'll just go ahead and use t as a parameter. In many cases, you know from the past, we were using theta a lot, and we'll do that some today. So for instance, we'll have a x coordinate, x of t, and a y coordinate, y of t. And what we're going to do is assume that t is in or contained in some parameter interval here, and r is smooth. Now, what that means is that the derivatives of x and y are not simultaneously zero. So what we're going to do is for t contained in the interior, I've used this before, interior of I, excluding the endpoints, we suppose that x prime is non-zero. This is from the smooth definition. So we actually need that for invertibility. So we're going to also talk about this when we discuss arc length, when we have the parametric representation. Again, all of this is revealed when you start looking at the manipulations you have to do. And so sometimes you may not really think, well, what do I actually need in order to recover the Cartesian derivative, and you just kind of just jump out on a limb and just say, well, I'll figure out what I need as I, navigate the journey, so to speak. So if we have a non-zero derivative on this interior of the parametric interval, we have invertibility, and that's a calculus definition of invertibility. So we use the invertibility of x on I and write. So we'll have y of x that we normally think of as the Cartesian expression of y, like y equal f of x, and write, in this case, y equal t of x. So the idea is that we have x written as a function of t, which corresponds to t written as a function of x. This is really the better way to do it. We are just slaves to the fact that we always like to write the independent variable the same. But when you actually construct the inverse function, you basically flip things around. X is written as a function of t, but the invertibility requires you or enables you to write t as a function of x. But again, we always like to graph things on the same set of axes, so we choose the same independent variable. But in doing that, students think that the process is just flipping variables, which it isn't. But again, it's all context. When you're doing math, you have to think, okay, so how is this going to help us? Well, we can use the inverse function theorem, which basically means that we can reciprocate the actual function to get its derivative. And that's useful. So I'll just say inverse function theorem. You can use all kinds of constructs. I mean, you can even think about implicit differentiation. There are all kinds of ways to look at this. So now, notice we'll have the inverse function theorem, and then, of course, this is a composition, so we're also going to use the chain rule. So I'm basically setting this up a little bit differently. I'm big on notation, but I don't like notation that's extra. Extra notation is just painful. I mean, we have enough to worry about when we're doing what we have to do to finish a problem. So I try to minimize notation only because I think too much is very confusing. So here's what we'll have. We can think of the derivative of y, like we just find y equal f of x, and write it this way. We'll just say the derivative with respect to x, and we'll just replace it with this, y of t of x. So I thought that it's always a better way. I change up some of the arguments to make them more realizable based on what I've already done. And this one's so easy to do. Now, remember, we like this Leibniz notation because it helps us to actually write the chain rule when we've got a independent variable x and t, and sometimes we need to differentiate them. So now you can see that we'll have the derivative of y with respect to t. So we do the so-called outer and then the inner, and then the derivative of t with respect to x. So you just move inside t derivative, then the x derivative by the chain rule. So this is where the Leibniz notation is extremely useful. Now you can see that this is where we can use the inverse function theorem. So right here, chain rule. And now we're going to use the inverse function theorem. So this is the derivative of y with respect to t, and then times will reciprocate the derivative of x with respect to t. And sometimes I teach the inverse trig functions this way. This time I actually did implicit because I thought it might be easier. But this is where the implicit function theorem is very useful, of course, appropriately evaluated. So now at this point, it looks like, okay, we've transferred from the x derivative. Now remember, back in Cal 1, we would say dy dx equals y prime, as long as it was clear that the variable of differentiation were x. Now, as we shift through here, we've got a bunch of t derivatives. So if you like, you can write this two ways. You can say we have the derivative of y with respect to t. That's just the derivative of the y coordinate of the parameterization divided by the t derivative of x. So the Leibniz notation basically gives you the variable of differentiation and the actual variable you're differentiating. So again, the t derivative of y divided by the t derivative of x, which kind of is important that x prime is non-zero. So we did need that assumption. So now, if you like, you can say, okay, well, I could really write this as y prime of t divided by x prime of t. And you'd be okay with that as long as you were denoting the actual variable of differentiation, where these would be the same. So often we want to look at this and say, okay, so now it looks like we start with y, and then we're taking the derivative of a function of y and we're dividing by the derivative of t. But now we're looking at this and saying this can actually be iterated, because now when we look at this, if we want to go up one more level of derivative, this is actually quite remarkable, and there's a lot of calculus going on here. We can see that the Cartesian derivative is actually a function of t. Okay, let me say that again. The Cartesian derivative that we're used to in calculus 1, the Cartesian derivative is a function of t. Well, and not surprising, because we've got the parametric representation here. So now if we wanted to, and you're looking at this and saying, this is crazy, and it should look a little crazy. So in order to get the Cartesian derivative, we take the ratio of the parametric or parameter derivatives of the representation here. That is y prime over x prime. And you're thinking, that is kind of unusual. So if we see that this is actually a function of t, there's nothing to stop us. I mean, we get slope with the first derivative, peaks and valleys, so to speak, with the first derivative test. So we're thinking, well, in Cal 1, we were often interested in the shape operator, the shape of the function, the concavity, points of inflection. So you're thinking, all right, well, can't we just move up to the second derivative? And like I said here, we can use this fact to get a very simple formula for the second derivative. So this implies that y double prime of x will now just be the derivative with respect to x of y prime of x. And so now this is a function of t, so we're back to here. So we can take this expression here and move to here and think of it this way. So this will be the t derivative of y prime. So we're replacing y with y prime. So let me just kind of box this too. This is what we're really using. And it kind of keeps us from getting lost in the prime notation. So we have the t derivative of y prime of x, which we just calculated there. And then, of course, divide by the t derivative of x. So this is where it actually behooves us to kind of stick to the Leibniz notation here, because again, we're taking the t derivative of the Cartesian derivative that we just computed by this ratio. And so now you're thinking, okay, so the second derivative gives us the first derivative of y prime divided by the t derivative of x. And so again, this would imply if we just kept going again, if we wanted y triple prime, and we'll just use a 3, this would be the derivative with respect to x of the second Cartesian derivative. And that would just be d dt of y double prime of x divided by dx dt, etc. So you can, this is inductive, but now we're not really going to go past this one, but you could use your n here and n minus 1 there. So this is the standard Cartesian, and so this is where the Leibniz notation actually comes in very handy. You can relax this a little bit and say, take the t derivative of this and then just do x prime of t here, since the x prime of t will always be the same without loss of any clarity. So for instance, we could say for n greater than or equal to 1, we could use Leibniz. We could say d n y dx n will be the t derivative. And we can write this way. We will say d n minus 1 y dx n minus 1. So of course, when we were doing it the first time, that would just be no derivative, right? Just plain old y of x and then dx dt. So this would be the inductive principle that we get from this. So the idea here is that even though we don't really care so much about all these other orders of derivatives, we do care about the first and the second. So this actually is quite important, but let me just make a comment here. If you're taking a vector function derivative, you're basically differentiating the coordinates and you're still getting a vector, okay, like you do in physics. But if you're interested in recovering the standard Cartesian derivative when you're in the plane, okay, then this is the way to do it. And that's really kind of different. And it actually makes sense because we did all that work in chapter 7 about arc length and surface area. And so if we describe a curve parametrically, we need to be able to do some things similar to that. That is, how can we strike a formula that will still allow us to compute maybe surface area if we revolve a curve about an axis, and with, for that matter, be able to actually compute an arc length when we have this type of representation. So this is kind of a new and a little odd type of calculus that we're doing here, and doesn't always get as much play as the vector derivative later on, but this is still quite important. And when we move to the polar coordinates in the plane, then we'll do the same thing. It'll again have more ramifications. So this is really the major topic of today. So let's look at how we can actually use this. Now, again, when you look at this, just be careful to preserve good notation. You don't have to be so specific that you're afraid to write anything down. But again, the notation will help you to realize what it is you're doing. So now let's look at an example. So here we want Cartesian derivatives. So compute, I'll just write in the relaxed notation, y prime of x and y double prime. So these are Cartesian derivatives. And then, there'll be a given value, in this case of t. So again, this can have its uses, and it can be extremely powerful. So for instance, say we have a vector function and we have t to the 1/2, and I'll write this down in more detail, and then 3t minus 1. So basically we have x is equal to the square root of t, and y is equal to 3t minus 1. And we want to compute derivatives at t equals 1. So when we look at this and we say, okay, well, if this is going to make any sense, at least while we're starting, t's got to be greater than or equal to 0. And if we start taking derivatives, then it'll have to be strictly greater than 0. So we can see now that it looks like as we start to take derivatives here, as a parametric representation, we have this, but then of course that will transfer to t greater than 0 as we start to take derivatives. And we found that out to be the case in Calculus 1. As you start to differentiate, the function expression changes. And so you may find that elements in the domain get kicked out, so to speak. So this is kind of where we're starting. So now let's just look at this. Let's just look at this as taking derivatives. So now x prime will be 1/2 t to the negative 1/2. And y prime is just 3, okay? So this implies, and you can do this in one step, but I thought I would separate it for now, just so you can get used to the idea of taking the t derivatives. Now, if we threw those into a vector, that would be the r prime. That would be the vector derivative. But now we're not stopping there. We're going to move to the Cartesian derivative. So now y prime of x will now be, as we've just derived, y prime of t divided by x prime of t. So y prime of t is 3. And if you like, you can write this way. This will just take everything downstairs. This is 1 over t to the 1/2. So we get the ratio of the two parameter derivatives. And so now we flip, and so we'll have a 3 times a 2t to the 1/2, or 6t to the 1/2. And then, of course, this implies if we compute derivatives at 1, y prime of 1. And we didn't have to do any work here. We might be given a point, and then we'll have to work backwards to find the actual parameter value. And so this would be 6 times the square root of 1, which is 6. So again, you're thinking you don't actually remember how we were analyzing the parametric representation and comparing things and going back and forth. I mean, those arguments were not always so simple, but one technique we found that was very useful is eliminating the parameter and then seeing how did that impact the actual function. What did we get, or what did we get with the parametric representation? Did we lose anything? Did we gain anything? Okay, we find, like I said before, that parametric representation can be so much more useful. And so here, what we're seeing is that we don't even have to solve for the Cartesian y of x. I mean, that's the beauty of this. This is like implicit differentiation. Remember, you don't have to solve for y of x to use implicit. This is basically the same. If you're given the parametric representation, you can get the actual Cartesian derivative that's a valid function without having to solve explicitly. I mean, obviously, if that's what you had to do, this would have no value at all. You just say, okay, well, we'll just solve for it, and then if you couldn't, you'd be stuck. So of course, this is a powerful technique. Now, y double prime, remember we iterate the formula. So we say the t derivative of what we just computed. I'll write this out for now because I want you to get used to the formulas. And then of course we can just do x prime here. We can relax that a little bit, or you can write dx dt if you like. So now we're going to take the t derivative of this. So we have t derivative of 6t to the 1/2. And then of course, x prime, in this particular case, it doesn't change. That always stays the same even as we move to the second derivative. So we can just go ahead and type that in. This will just be what? 1 right here, either form, 2t to the 1/2. And so now when we take the derivative here, we've got what? 6 times 1/2 t to the minus 1/2. And we have 1 over 2t to the 1/2. But notice we're just getting the same thing. These absorb, but let me write it so it's easy to see. So we get 6 times 1, 2, t to the 1/2. 1 over 2 t to the 1/2. And of course, these absorb. And we just get 6. So therefore, that's a constant function. Y double prime of 1 is just 6. So this is a little bit odd at first, but once you get the hang of it, it will sink in. Again, computing the Cartesian derivative from the parametric representation. So let's look at another one that has some trig in it, and then I think we'll do a tangent line just to kind of review some topics from Calculus 1. Tangent lines are always fun. And that's what you did every time you learned a new derivative in Cal 1. You compute a tangent line just to practice the derivatives. And that was fine. I guess that's a good way to practice. So now an example here will give the following. That is, we have r of t equals 2 plus secant. Well, in this case, it's going to be a theta, secant theta. So make that, I made my t into a theta. That's easy to do. And then 1 plus 2 tangent theta. And we're going to want to compute our derivatives at the parameter value theta equal negative pi over 3. So again, when we actually do these computations, let me move Professor Ron over a little bit. I'm in the way. So now, again, here's our x of theta. And here's our y of theta. So if you like, now we can actually look at this as we more formally that we kind of know what's going on. So for instance, we'll say y prime of theta will be, well, how sad. Let me put my x here. Again, this is the Cartesian derivative. And this will be the derivative of y with respect to the parameter theta divided by the derivative of x with respect to the parameter theta. So you can relax the notation a little bit here since now we know what the theorem says. So now let's just go ahead and do this. So y prime, again, we're going to get a 0 and the derivative of tangent is secant squared. So we get 2 secant squared theta. And then of course here we get 0 and the derivative of secant is secant tangent. So now it looks like one of the secants absorbs. Now, one thing that's interesting about this is that now this reminds us of what we were doing with our trig integrals. So we get 2 secant theta over tangent theta. So when we would integrate things like this, we would just kind of rewrite it maybe in terms of the sines and cosines, or just think of what this actually equals. Here's another trick. Remember, you learned this back in pre-cal. You would say tangent theta, you don't have to do this, is what? Sine over cosine, right? But then you could just write this as secant theta over what? Cosecant theta. That always blew everyone away. Oh, I see what you're doing. Now you're right. You know, cosine is secant and sine is cosecant, but putting them in the right dispositions and all. So we could say this is what? 2 secant theta. And this will give us secant theta, cosecant theta. And of course, the secants absorb and the theta just flips. So we get 2 cosecant. So that's like 1 over x equals x times a 2, right? So that's one way of looking at it, but you certainly could just write everything in terms of sine and cosine. No big deal there. So now again, we have our Cartesian derivative as a function of the parameter theta. Again, that's the kind of the linchpin of why all this works. So this implies that y prime, the Cartesian derivative at negative pi over 3 will be 2 cosecant negative pi over 3. Now, if you like, the cosecant function is odd, so this will be a negative 2 cosecant pi over 3. But of course, this is just the reciprocal of sine, so that'll be 2 over root 3. So we get negative 2 times 2 over root 3. And that gives us a negative 4 over square root 3. So now we're doing pre-cal. You try to convince your pre-cal students that this is actually important and that they don't ever believe you. And then they get to Cal 1 and Cal 2, and then they're like, oh, yes, I should have spent more time on pre-cal. Now, for instance, let's just go ahead and see what we can get for the second derivative. So we have y double prime of x, just to practice. We'll take the t derivative, or in this case, the theta derivative of here, the Cartesian. So I'll write it out, d theta of the Cartesian derivative that we just computed divided by dx d theta. So here we have d theta, and we can just type it in, 2 cosecant theta. And then, of course, the derivative of the x, that is the theta derivative of the x coordinate, we've just computed there. That's secant theta, tangent theta, so we can reuse it. So now the derivative of cosecant is the negative what? Negative cosecant cotangent. Just like we do up here. And so we get secant theta, tangent theta. Now, when you look at this, you can think of this kind of similarly to what we did here, because we start getting reciprocals and things. Now, if you look here, this does the same as we did before. Let me just add something. So this implies if that's tangent, then cotangent, just a little sidebar, is cosecant theta over secant theta. So that we can just take reciprocals and get that. So now this equals, this is kind of a fun little problem, even though it's not that important. We've got what, -2. So I'm going to use this, but I'm going to write it out so you can see it. Cosecant theta, secant theta. And now, of course, this is 1 divided by 1 over cotangent. So we have cotangent theta. Just to practice our trig identities, that's all. So now we can do cosecant over secant as cotangent. So we get -2 cotangent. And now this flips and we get 2 copies of cotangent. So this gives us -2 cotangent cubed. Kind of odd looking. So when you start doing the trig derivatives as far as the Cartesian and all, you just have a lot of simple identities. But of course, there's nothing to stop you from just turning everything into sine and cosine. You get the same results. I just think it's interesting sometimes to look at these functions differently, just because as you do your trig integrals, you find yourself having to do this. And so this is really good review for those techniques that you learned back in chapter 8. So now this implies that y double prime, again, of -pi/3, this will give us, so we can factor, so we have -2, so we have cotangent of -pi/3 cubed. Again, just like the tangent function, the cotangent function is odd. So this will give us a 2. And of course, that gives us a -1 cubed, which is -1, right? So we get -2 times a -1 cubed. And now we have cotangent of pi/3 cubed. But cotangent is just the reciprocal of tangent. So tangent of pi/3 is √3. So we're going to get 1 over √3. So this will be what? 2 times 1 over √3 using our unit circle cubed. So that'll give us a 3 √3. So we get 2 over 3 √3. Again, cubing the √3 to give us a 3 √3. So this is, again, just a lot of pre-cal, but important pre-cal. So what we can see again is that this is kind of just a little exercise in pre-cal and cal 1. Oh, here. Let me move this over a little bit. There we go, so I can focus. Now I can make my screen with this thing a lot bigger, but I don't want to push the focus button to where I can't see it. Zoom crowds my screen. Now that I've got a bigger screen, I still have to, I'm getting too spoiled because I make everything too large. So I'm going backwards. So what we can see here is that when you're doing the Cartesian from the parametric representation, it's just a you know, very, fairly perfunctory, just work through the simple calculations, but important calculations that tie everything together. That's kind of what's nice about calculus. It all fits together very neatly. So what I promised I'd do is let's try this out with a tangent line. And so what often will happen is that you're asked to compute the equation of a tangent line at a given point. And so you got to work a little harder. So it says in this example, compute. So this is like Cal 1 and Cal 2, Calculus 1 in Calculus 2, because it looks like we're doing more Cal 1 now. So compute equation of tangent line at the given point. So here, again, I'm just giving you the vector notation that you're going to use later. This is just neat. So we get what? 2 cotangent theta and 2 sine squared. This is always a good example. And we want to compute the tangent line at this point, 2 root 3 1/2. So the idea, again, this is x. So this is x of theta. And this is y of theta. I minimize the notation. I don't call this f and g, and I'm sorry, I can't do that. There are things that putting extra letters in a problem is just not good, and it doesn't make it easier when you do it. And I don't agree with every mathematician. Certainly not every mathematician agrees with Professor Ron, but the idea is I only use the notation we need for clarity. Excessive notation is excessively difficult, and we have enough to deal with. So again, I'm minimizing the notation. So notice here, we know how to compute a Cartesian derivative that we've just been practicing, but here we're given a point, and so this point's not going to do much good for us when we need to actually find the derivative at a value of the parameter. So what we can do is work backwards. Now, when we solve trig equations, we have to find a parameter that works for both. So we'll just use a little pre-cal to work it backwards. So in this case, I'll just write find value of parameter theta. And a consistent one. Just find one that works and we can move the problem forward. So first we have what? 2 cotangent, just some real simple trig equations from pre-cal. 2 cotangent theta equals 2 root 3. So this reminds us of the last problem. That's why I thought it was a good one. So the 2's absorb. So cotangent theta equals root 3. Now, of course, we spend more time with the inverse tangent, so we'll just reciprocate both sides. So tangent theta equals 1 over root 3. Just reciprocate both sides. So now theta, we can find a unique answer here. Theta will be the inverse tangent of 1 over root 3. Again, that's when we get 1/2 divided by root 3 over 2. And of course, that's pi over 6. Now, of course, we can add multiples of pi to this if we need to move things to a corresponding t value. But if we can get this to work for the other coordinate, then we're fine. Just keep in mind that you may have to make some adjustments via the period to get a consistent value of t. And that's what you're used to, because trig equations are just that way. So now for the other parameter here, or the other coordinate function, we have what? 2 sine squared theta equals 1/2. So this is quadratic in sign. So of course now, we can divide by 2. So this will be what? Sine squared theta minus 1/4 equals 0. So just, like you do in pre-cal, get a leading coefficient of 1, divide by 2, and put everything on one side, and then of course factor it. So now we've got sine theta minus 1/2 times sine theta plus 1/2 equals 0. So clearly we have what? Sine theta equals 1/2, or sine theta equals negative 1/2. So now that this one's going to be good. So theta will be the inverse sine of 1/2. Again, we know that's a unique value, and the inverse sine of 1/2 is pi over 6. Now, of course, if you had solved the other side first, you're going to have what? Theta is equal to the inverse sine of negative 1/2, which will give you negative pi over 6, which is fine, but that's not going to be consistent with this. So when we actually work these problems, we find a consistent value of t. That's what's going to move the problem forward. So we select t equals pi over 6. So that's the only hiccup that we have to deal with. It's not hard. It's just that sometimes we're going to have to do some busy work with these problems, and don't look at it as being an issue. It's like when you work with conic sections and you've got to do a lot of algebra to figure out the standard equation, especially if it's been translated, and no one wants to do it. I'm like, well, I mean, it's just part of the ball game, so to speak. It's part of the strategy. So now we've got the value of theta, in this case, the parameter, like we did in the previous problems. Remember, the previous problems, it was given to us. Here we had to figure it out. And now we can construct the tangent because we can now compute the Cartesian derivative. So y prime of x will now be y prime of theta divided by x prime of theta. So again, we have the derivative. So if you want, let me write this out since it's kind of far removed. So we'll do d theta 2 sine squared theta, and then d theta of 2 cotangent. So now we have what? Chain rule. So that'll be 4 sine theta times cosine theta. And then, of course, the derivative of the cotangent is the negative cosecant. So we have negative 2 cosecant squared theta. Now, of course, that'll give us a negative 2. And if you like, we can rewrite this. So this is going to be sine theta cosine theta, and this will be 1 over sine squared. So we can reduce this. So now this will flip up. So we have negative 2 sine theta cosine theta times sine squared. So that gives us 3 copies of the sine squared. Again, simple calculations, but you always check everything you do. That's just the nature of the calculus, as you well know. So here's y prime of x. That's our Cartesian derivative. So now we can actually evaluate it, if you will. So in this case, we have the slope will be y prime of pi over 6. I'll do this here and then I'll move to another page since I'm running out of room. So again, our value of t, well, I say select t, we know that's a theta. Select t, select theta. It's great that I can make the thetas, t's into thetas very easily. So just, this is the parameter, again, parameter value. So here we have what, -2, and we have sine of pi over 6 cubed cosine pi over 6. So this gives us a -2, and of course sine of pi over 6, our friend, that's 1/2. So we have 1/2 cubed, and then cosine of pi over 6 is square root 3 over 2. So this will give us a -2, 2 cubed, right, times root 3 over 2. And of course, the 2's absorb here. So this gives us a -root 3 over 2 cubed, or 8. So that gives us the slope at the value pi over 6. So we're doing the same things. Nothing has changed. Everything's pretty much the same. Let me just move the computation to another sheet. So at this point, we've got all the details, so to speak. Now let me go back to the top. So let's just write here. This is what I always like to do when I'm what is it? I think when I'm doing, what is it? Maybe it's been in this class. Remember, I'd always say summary. I think I did this more in pre-cal. So now we have a slope. So now we're back to algebra 1, a slope of -3 over 8. And then we have the point, remember from the very beginning, 2 root 3 1/2. So 2 root 3 1/2. So use point slope. So this gives us y minus 1/2 equals -root 3 over 8 x minus 2 root 3. So now we can just multiply this out. I mean, it doesn't matter at this point. So you can take the 1/2 over if you want. And then we get what? A -root 3 over 8 times x. And then of course we get a positive from the negative. So we get, what is it? Plus 2 root 3 squared over 8. So we've got -root 3 over 8x plus 1/2. And then of course here the 2 absorbs into the 8 to give us a 4. And so we get plus, in this case, 3 over 4, since the square of the radical 3 is 3. And let me get a little focus here. It looks better. And so now we can add these if you like. So we have y equals -root 3 over 8 x. And let's see that what plus, so we got a 4 clearly. And so that'll be what? A 2 plus a 3, if and only if y equals -root 3 over 8x plus 5 over 4. And of course, you could multiply everything through by 8 and throw everything on one side if you wanted. I don't think it really matters. Of course, it just really depends how it's listed. So here, the key is just, again, using an old strategy from Calculus 1, which we actually borrowed from Algebra 1, point slope. I mean, it's amazing. I think you really learn your algebra when you take calculus because you're really forced to understand it. So again, just very maybe somewhat boring calculations, but important calculations to get used to this new construct. Now, with that, we have an added, I guess, bonus with this parametric representation of the Cartesian derivative. It can allow us to compute points of vertical and horizontal tangency in a way that focuses on the curve. But again, we've got busy work too, which is maybe not the best thing. So for instance, here's something that we just note. I will showcase this in an example, but we could say horizontal tangency. Horizontal tangency. And then we can think vertical tangency. If we're thinking of points. Now, in order to characterize that, we just remember, and of course I'll use t again, so I'll probably write t for theta again. So y prime of x, at least using the t, is the ratio of the t derivative of y to the t derivative of x. Or we're thinking of the parametric representation. So again, this gives us a new way to analyze horizontal tangency. So this will make sense. Of course, we've got a smooth curve. So in this particular case, we would have the y prime 0, but the x prime non-zero. So we say y prime of t equals 0 for a horizontal tangent and x prime of t non-zero. Now remember that we might be at points where the x prime is 0, and that's not a point where the curve is smooth, but remember we do piecewise smooth. So we do our calculus to that point, then we just kind of say, all right, now we have a new interval because piecewise smooth. So every time we're looking at a curve in terms of calculus, we're assuming the smooth nature. And if we have to avoid a problem, you know, we don't even look at maybe a vertical tangent as being that huge of a problem. We just kind of do our calculus to that point, and then we set up a new interval, avoiding that. But the cusp is the biggest problem, the point or the cusp, like we saw in the asteroid or the epicycloid, where you really do have a pathology. So here we think of horizontal tangency comparing to this where y prime of t is 0 and the x prime is non-zero. Vertical tangent would mean that we would have x prime of t equals 0 and y prime is non-zero. Again, that will help to preserve the smooth, but we still have an issue with the Cartesian derivative. You know, it's when the tangent line is vertical. The curve may still have that smooth look because we're satisfying the definition, but we can't mow over it if we're, you know, thinking about, okay, we got an issue here, but it's something we can overcome. When we think about arc length, we can't just mow over that. We already know that now. So again, just always think piecewise smooth. If the curve is well behaved enough, it'll have plenty of sections where it's nice and smooth, and then we can just kind of hop over the inconsistencies and then join them all back together like we do when we integrate. But the key here is that if they're both 0, that is indeed a pathology and would not be the case for either of these. Notice here, and this is important, students often make mistakes with this because they're not assuming that this is an and, okay? You must have both of these, okay? And if they're both 0, then that's a pathology. That's a point, a corner, or a cusp. Note, when we have x prime of t equals 0 and y prime of t equals 0, that's even worse. This is a corner cusp. This is what we call the pathology. All right, and this is not part of either of these. Okay, so if you've got this, you have neither of these. And we need to be careful about that. That's, that's just called like, okay, I'm going to jump on the parametric derivative deal and not worry about what I learned in my previous 5 years of pre-calculus mathematics. We often make careless mistakes because we just think that now we've risen above it, but we haven't. We do all the same stuff we did in our general math class or our number theory class, so to speak. So if you look at this example, we can say, or this observation, we can use this to actually solve problems. So let's look at an example of this. So we'll kind of keep this in the background. So here's an example. We'll just say compute, let me not try to say compute and point at the same time. Compute points of horizontal and vertical tangency. And we have, in this case, I'll just write these out. X of theta is cosine theta. At least we can use even and odd, but I tell you, these could get, more tedious if we change things up. And here's a good example. And we have sine theta minus theta cosine theta. This is a nice example I like to do because it kind of covers all the bases. And theta, in this case, will be restricted. So we're going to look for these points, so to speak, between negative pi over 2, negative 2 pi and positive 2 pi. Let's just say it that way, a little bit more broad than I initially thought. About right here. So twice around the unit circle, so to speak. So now, again, we're going to use the litmus test and then compute the points. So now first we'll say, okay, what does the Cartesian derivative give us? And we know that this is the case. We have y prime of theta divided by x prime of theta. So we'll go ahead, this just kind of gives us the roadmap. So let's go ahead and look at this, and we'll think of the horizontals first. So let's just go ahead and look at the y prime equals 0. So first, for the horizontal, we'll have y prime of theta equals cosine theta. Then by the product rule, the derivative of theta with respect to theta, that's minus cosine theta. And then, of course, we'll have minus theta times the derivative of cosine, which is the negative sign. So these absorb, and we get what? Positive theta sine theta. And so now we see y prime of theta equals 0 if and only if theta equals 0 or sine theta equals 0. Well, equivalently, what is that going to give us? Well, we already have 0, and then, of course, the sine theta will be 0 at the axial values, 2 pi, pi, negative pi, and negative 2 pi. So this will be theta equals 0. We'll say negative 2 pi, just multiples of pi, so to speak, but we're restricting negative pi, positive pi, and 2 pi. So that gives us this. And then of course, we'll check this out, see if we have to exclude any of this. And so this is horizontal, at least for now, okay? And then for vertical, we have x prime of theta. So we'll take the derivative of x of theta. So this will be negative sine theta plus product rule. So that'll just give us a sine theta when we differentiate with respect to theta. And then we have plus theta times the derivative of sine, which is cosine. So of course these absorb very nicely. So we get what? Theta cosine theta. So there's our derivative of theta, x with respect to theta. So we have x prime of theta equals 0 if and only if, zero product, theta equals 0, or cosine theta equals 0. And of course, cosine theta is 0 at the odd multiples of pi over 2. So we learned that from pre-cal. So we have theta equals 0. So we'll get negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. That's when you're solving trig equations. Remember that these are axial. These are not in the quadrants. These are on the axes, and the quadrants don't include the axes, as you well know, even though my pre-cal students don't want to believe that. You learned everything you needed to know in college algebra and pre-cal, and if you don't know that now, you should. Okay, so when you look here, you can see that we do have an issue. We've got zeros that kind of get in the way. For instance, we see that these are offset. Okay, so if we look at these and we look at these, we have a 0 of x prime that's not a 0 of y prime, okay, and vice versa. But here's an issue here. That's a pathology. So this will be excluded. Excluded. So that goes back to what I wrote here. We avoid this, okay? And that's why this is a really good example. So now if you want, let's just go ahead and write down some of these points. So we'll just go ahead and start with the vertical and then finish with the horizontal. So how do I want to write this? Points of vertical tangency. Just a lot of bookkeeping. So now, if you will, just so we can see everything, x equals cosine theta plus theta sine theta, and y equals sine theta minus theta cosine theta. So let's just go ahead and do this. I'll do this in blue. So for the vertical, we'll just start here, show you how this works, and then I can summarize some of the others, but I'll do several of these so you can see how it works. Maybe I'll just do all of them. We'll see. So this is like backwards of the last problem where we were given the point. Now we have to figure out the point. So now we say, okay, negative 3 pi over 2. So this just says x of negative 3 pi over 2. So this is going to give us cosine. Well, this is where we can be a little lazy, and I'm going to be just a little lazy, but not a lot. Okay, these are axial values. That cosine is clearly 0 there, so I'm not going to write that down. So that we'll just use the fact that for all of these values, the cosines are 0, so we can just forget about them. So we have 0 plus, so we have negative 3 pi over 2, and then we have sine of negative 3 pi over 2. So again, just remember all these cosine values will be 0 at these values. So not to shirk the responsibility, but I think you easily see that. But now, of course, the sign is odd, so we get negative 3 pi over 2 times a negative 1, and that gives us sine of 3 pi over 2. But of course, sine of 3 pi over 2 is negative 1. So like I say, this gets a little bit arithmetic. So we have negative 3 pi over 2 times the negative 1 times the negative 1. So 3 negatives gives us a negative. So this gives us negative 3 pi over 2. So there's the x coordinate. And now y of negative 3 pi over 2. Well, of course, this is just going to be 0 because of the cosine term. So this gives us sine of negative 3 pi over 2 minus the 0. So again, just like we did before, this gives us negative, it's odd, sine of 3 pi over 2. So we have what, negative 1, and sine of 3 pi over 2 is negative 1. So we just get a positive 1. So the point for t equal negative 3 pi over 2 will be negative 3 pi over 2. And let's just see here, sine, where did I write this? Let me just check something. So I've got negative 3 pi over 2, and yeah, that looks good. So here, notice, and this is interesting because when you think about this calculation here, when we say sine of negative 3 pi over 2 and it's odd, we do get the positive. So yeah, that looks good. Okay, so now let's look at, what's the next one here? Let's go ahead and do t equal negative pi over 2. I thought these were kind of neat. So let's see, in this particular case, let's see, I've got that. That looks good. So we've got what, x of negative pi over 2. Again, this will be a 0, so we'll just say 0. And then we have plus negative pi over 2 sine of negative pi over 2. So that gives us negative pi over 2. Of course, this factors, it's odd, so we get a negative 1 times sine of pi over 2. And of course, that will be 1, so we get a positive pi over 2 times 1, which is positive pi over 2. So that gives us our x coordinate. And then y of negative pi over 2. Again, this term will be 0, so we'll just go ahead and leave that out. So this is sine of negative pi over 2 minus 0. So this gives us negative sine of pi over 2, which is negative 1. Sine of pi over 2 is 1. That gives us negative 1. So now we get the point pi over 2, negative 1. Keep going. This is good. These make great test questions. I want you to know how to do this. I used to just kind of throw this caution to the wind, and I would ask students to do it and they couldn't do it. The work was ridiculous. So now let's keep in track what we've got. So now we've got what, pi or t. Now, of course, I've been writing t in all of these. And of course, these are all thetas. I told you I would do that. Isn't that funny? I'm a creature of habit when it comes to the parameters. I do all my theory with the t's, and then we've got all these thetas. So we have theta equal pi over 2. So I'm going to cover this part up so I can see the equation right here. So now we've got what, x of pi over 2. That'll give us a 0 plus pi over 2 sine of pi over 2. So this gives us pi over 2 times 1, which is pi over 2. And then y of pi over 2. Again, we're going to get what? Sine of pi over 2. And then, of course, this will be 0, so minus 0. So that's just 1. So that one was easy. So we get the point pi over 2, 1 for that value. Okay, now theta equals 3 pi over 2. See how long I can write it without doing another t. How funny. So now we have x of 3 pi over 2. So we'll use our equations. So we've got, again, a 0. So we have 3 pi over 2 sine of 3 pi over 2. So this gives us 3 pi over 2. And of course, sine of 3 pi over 2 is negative 1. So that gives us negative 3 pi over 2. And then y of 3 pi over 2. Again, the cosines will be 0. So that just gives us sine of 3 pi over 2 minus 0. And that just gives us a negative 1. So that was easy too. So we get negative 3 pi over 2, negative 1. So this is how you compute these. So notice with these examples, we have 4 points of vertical tangency. Now that you've gotten the drift of it, I'll summarize the rest because I actually worked out the other ones. So for the points, and you can work through this, but I think you get the drift now, and I don't want to bore you to tears. Points of horizontal tangency. Again, I wanted to work through these simple calculations because for some reason it tends to get lost that you just have to do basic pre-cal. That's it. So we've got interesting results here that when you think about this, you know, there's sometimes like this disconnect between the parameter and the point. So you have to be able to toggle between the two. So for the points of horizontal tangency, I've got theta equals negative 2 pi, and you can easily compute this. You'll get the horizontal tangent point is 1, 2 pi. The 2 pi's and all that, they're easier to work with. And then theta equal negative pi. We got a point in this case of, let's see, what did I get for this one? Negative 1, negative pi. And then for theta equals pi, I got negative 1 pi. And then for theta equals 2 pi, I got 1 negative 2 pi. And I wrote in my notes, good exercise. Again, just check the points. And if you can remember, when we were computing these, this was x equals cosine theta plus theta sine theta. So if you rewatch the video, you can pause it here and compute these. Again, I think you know how to do it. So we get 4 points of horizontal tangency. So again, when it comes to using the parametric representation of the Cartesian derivative, we get really additional information that is of great use to us. But again, we still have to do some of the standard busy work that we did in pre-cal. Okay, I like this problem. It's a good example, and it doesn't need to be underestimated. Unfortunately, sometimes I underestimate the arithmetic. That is exactly why I do everything by hand, because with me assuming that students can just do the computations is not always correct. It's good for you to see the computations. So check those for the horizontal tangents as you work through your notes. Now for arc length, this is actually, you're thinking if we've got parametric, how do we make our formula for arc length work? So remember, we're going to have R of t equals x of t. Now, of course, I'm going back to t, and I'm not going to want to return to theta if I have to see it again. How tragic. We're just creatures of habit. And so we're going to say smooth for I, and we're going to say equal AB to give it the flair of a interval. We like AB when we're doing our calculus, especially with integrals. And we'll just say without loss of generality, we're going to need x prime to be non-zero. So we'll just say it's positive for t element of the interior of AB. So we don't want to divide by zero. So, and the key here is that we're okay at endpoints. We just, on the intervals of content is where we need this. And so this is smooth. So we're going to make this assumption. So now remember that before, when we looked at the radical, we had arc length equals something like this, A to B, and we'd have the 1 plus y prime of x quantity squared to the 1/2 dx. So that's what we want to transform, and it's actually quite easy to do. So what we can do is the following. And if I need a little extra time on Wednesday to complete this, I'll use it before I do some review. This information is extremely important, and I don't like to shortchange anything. So when you look at this, you're thinking, okay, how can we move forward? Well, let's just look at this part right here. So this implies that 1 plus y prime of x quantity squared, we can now do the Cartesian derivative that we derived. So this will be 1 plus y prime. And now I'm going to put the t's, but then I'm going to relax it because writing the t's forever will make us crazy. We're assuming t derivatives now. Or maybe I'll just do it so it's clear. So now we can see that we actually substitute for the Cartesian derivative, the ratio of the parametric derivatives as we get from here, as we've been doing forever. So this gives us 1 plus y prime of t squared x prime of t squared. Get a common denominator. Now you see why we need this. You know, we don't want to divide by zero. So we have what? X prime of t squared. And we have x prime of t squared plus y prime of t squared. So now we're looking at this and saying this is making a lot of sense. And again, we've got our assumption here. And then obviously here we know that x of t is our parametric x coordinate, and that'll allow us to actually rewrite the dx. So this implies that dx equals x prime dt. So we'll use that. So now look at the square root. This implies 1 plus y prime of x quantity squared square root will now be the square root of this. And if you like, let's just go ahead and tack on the dx. So we'll have x prime of t quantity squared plus y prime of t quantity squared. This is important. I mean, I don't always do all the theory, but this is extremely important, and you need to see this. 1/2, and then dx will just be x prime dt. So of course, now we have the square root upstairs. I'll just write that as the bracket, x prime of t quantity squared plus y prime of t quantity squared to the 1/2. And of course, downstairs, we just have the absolute value of x prime. But of course, this is just x prime by hypothesis. This part just equals x prime. And of course, the x primes absorb. And this gives us x prime of t quantity squared plus y prime of t quantity squared square root dt. And of course, I don't want to discriminate. The 2 stays inside the radical. So if and only if arc length, and of course with the, we've written it so that the parameter interval looks like the Cartesian interval, you know, you can call it alpha to beta if you want, but I didn't. Now what we're saying, since I used this, let's write it this way, because I bothered to do that, so I need to write this. So I'll say alpha to beta. And so in this case, we would see that the corresponding parameter interval, we'll say AB corresponds to alpha beta. This is Cartesian. Since I bothered to write that down, I need it. And this is parametric. So we get something like this, because these won't necessarily be the same. So we have x prime of t quantity squared plus y prime of t. Said I was going to leave the t's out, but I put them in anyway. dt. So we've got this rather strange looking Pythagorean integrand. It's not a surprise, but you can see that it's not hard to remember. So now, instead of doing the 1 plus the y prime squared, where we squared the Cartesian derivative, we now take the sum of the squares of the parametric derivatives. And this is all based on the Cartesian derivative that we derived at the beginning of the lecture. So there we have it. There's our parametric form of arc length. So let's use it. I'll tell you that the work that we have is actually very interesting, because what we're seeing is that as we develop these new ideas, they're related very intimately to what we've already worked with. So we don't have to start from scratch, which is nice. That's a blessing. So what I did, I looked for an example that was different from the asteroid. I mentioned that, remember, with the cubes, you know, with the trig functions. I thought I would look for something that's a little bit different from that, because that's in my Blackboard notes. So here, I found an example that uses one of your integral formulas. So R of t is going to be, again, the square root of t for the x coordinate. And this looks very familiar, doesn't it? You know, we did this with the Cartesian before, and you're thinking, well, that was easy. This should be real simple. Well, it didn't turn out to be so simple. So I thought this was kind of a blast from the past, which it actually is. And here, you know, we analyzed this before, if you remember, and now we're going to look at it in terms of arc length, and we're going to let our parameter interval, Arthur is nice to you, we're just going to let it run from 0 to 1, okay? So we usually have to make some type of if we present the parametric relationship, then if the parameter interval is already there, we're fine, and we don't have to do any further translation. But I can't just say that the parametric interval is going to be the same as the Cartesian. That's clearly wrong. That's why I had to make that change to alpha beta, just because we don't necessarily know that. And in general, they would not be the same. So now we want to compute arc length. I thought this was a good one. So now let's just go ahead and look at this. So we have x equals t to the 1/2 and y equals 3t minus 1. Easy derivatives. So we have x prime equals 1, well, 1/2, 2 to the negative 1/2. So we know that looks like this. And then y prime is just 3. Okay, so let's just look at this. So we've got what? X prime squared, we'll just do it piecemeal, plus y prime squared. Again, here I can relax it a little bit because we're assuming, and how nice, I've actually got a problem where the t's are the parameter as opposed to theta, so I don't have to back up and say, all right, that t should be a theta. So this will give us what? 1, we have a 4, and then we have a t. And we'll look at this a little bit differently to make it work in terms of the derivative, the antiderivative, just to change it up a little bit. Plus, what, 3 squared, that's a 9. So this will give us 4t, and we'll get what? In this case, we'll get what? A 36t plus a 1. Now, this is where you can look at this and write this in a way, I think this will work, that is actually very user friendly, because when you look at this, you're thinking maybe I should have preserved all of these square roots, and that's the key here. Notice we again can do this because of where our parameter lives, and we don't even have to throw any negatives. So we can say 6 square root t, you can see what I'm doing now, square, plus 1 squared, or just 1 for now. And then, of course, downstairs, we'll just have 2 square root t squared. Okay, well, mix and match, right? So now we've got what? 6, and I'll just write this t to the 1/2 for now for ease of computation, squared, plus 1. And then I'll bring this over to the side. And so we've got 1, excuse me, 4, excuse me, square root t. And then I'll square this. Let's see how I want to write this. So let's see here. Yeah, this looks good. This is squared. Let me write it this way for now. Then I'll square root it. Now, take principal square root. So this implies x prime squared plus y prime squared 1/2 dt. So this will give us 6t to the 1/2 squared plus 1 to the 1/2. And now we get the square root here. Again, don't need any negatives, times 1 over 2 root t. So now, and then dt. So now you can see that if we make the effort to do this when we apply the square root, we have a nice substitution. So at this point, u would just be 6t to the 1/2 du. Again, 1/2 times 6, that'll be 3 t to the negative 1/2 dt, or du equals 3 over the square root of t dt. So now we can see we can factor the 2 downstairs, put in the 3, and pay for it. So this implies S will now equal, and let's just see here, we've got 0. So let's go ahead and figure out these. Let me do these in red. U of 1 will just be 6. Again, 6 times 1, and u of 0 is 0. I know I've broken this down into bits and pieces, but I want you to see this. This is an excellent example. So we have 0 to 6. And now I'll factor the 1/2, make it table ready. But then I'm going to need the 3 here from the differential. So I'll pay for that also. And then we've got 6t to the 1/2 squared plus 1/2. And now we're good to go with our differential, 3 root t dt. So now we can see we've got our du, we've got our special integral formula, and I actually pulled out the integral table, which I'll reference here. We've got our trig sub, but we don't have to do trig sub anymore because you can, when you're doing a problem within a problem, you can actually use your integral table unless I tell you to use trig sub. So this gives us what? 1/6. And this is where, if to be completely correct, let me not put the 6 up there yet. Let me preserve this, and now I can go to this. Technically, well, I'm fastidious, so that shouldn't be surprising. So we have 0 to 1. Now we have 0 to 6 as we convert completely to this. We're still in the t here. So I changed these, but the 1 would have to be preserved until I converted everything to u, of course. So we have 0 to 6. So we've got the square root, make it look nice and calculus-like, u squared plus 1 squared du. Now, how nice. So what I did, this is from your integral table. It was formula 26. Too many paper clips. So formula 26, we've got the u squared plus a squared. So we have, again, this is trig sub, but this was one of our special integral formulas. 1/2 u, the radical with the plus. Remember, with the plus, you choose the upper plus a squared right here. So I'll write that down. So this is a special integral. So use number 26. No need to break out the big guns with the trig sub. You'll do that when I ask you to do it. Otherwise, you can use the integral table with this. So we can substitute the u, and of course the a is 1 here, so that makes it easy. So we have 1/2 u square root u squared plus a squared. You do these a lot in Cal 3 because you can't avoid these kinds of integrals. So this is good preparation for that. So u squared plus a squared plus a c. But of course, that'll go away. So let's fill this in. We'll be done with this. And then I'll say a little bit about the surface area. And if I don't have time to finish those examples, I'll just complete that at the beginning of next lecture. So you notice, obviously, if we have an arc length, then we'll have the surface area, which is the companion formula from chapter 7. So now this will give us what? So here, just write, this is a really nice example. A equals 1. So we just fill it in. So we have 1/2. So we have u. So we have u squared plus 1. 1 squared, 1, right? 1/2. Plus 1 squared. So we have natural log u plus square root u squared plus 1. The old integral table is our friend, of course. Always has been, 0 to 6. We pay dearly to get all these nice formulas. And so now we get to reap the benefits, especially when I allow you to use the integral table, which you should already have printed out so you can use on your test, which is legitimate, okay? Not the computer algebra systems, which are forbidden. And I don't want to see that on the next test. So please do not put yourself in an awkward situation using things that are not uh, uh, allowed for the test. Just remember that. So now what do we get? So we have what, 1/2. So we've got 6. So we have what, 6 squared plus 1. So that's the square root of 37 plus natural log. And then we have 6 again plus square root of 37 plus square root 30. So easy. Don't have to work at all. And then minus 1/2. So we'll do the lower limit, which will zero out everything. So we have a 0 here, the 0 times the radical. So that's a 0 plus, then we have natural log. Of course, so that'll give us a 0. So we have 0 plus, so we've got 0 plus 1 square root of 1. So that's just log of 1, which is 0. So all of this is just equals 0. So what does it give us? This part. So this gives us, I'll write this in blue, 1/2. You can leave everything inside here or multiply and get a 3. I don't think it really matters at this point. So 1/2, 6 square root 37 plus natural log 6 plus square root 37. So that's kind of a nifty problem. And you look at this problem and again, like I say, I broke it down into a million pieces just to make sure that you understand it. The key here, and the reason being, is that you start thinking this way because you know you have to take square roots. And I started doing this, not reminding you that we have to take the principal square root to move the problem forward. So if it doesn't look like you've got something really nice and you've got just these first uh, uh, powers here, this is always a good trick. It works and it moves you into the special integral formula. So I thought this was a neat example. Seems so simple, and then you're like, okay, as you start working with arc length, that there's always a thorn in your side. The Pythagorean integrals are never easy, and then of course the elliptic integrals are worse. And when you take certain engineering classes, you will be introduced to elliptic integrals, and they keep you busy. But this is where we start. Okay, now for the extension here, you know, we think about, okay, what if we take a curve and revolve it about an axis? Then we need the distance to the axis of revolution, but we can easily do that with the parametric representation. So that again is a freebie. So for area of a surface, we include, remember that we include the distance, to the axis of revolution. So we don't have to start from scratch here. You know, again, we can breathe a sigh of relief. Number one, we'll say revolution. Again, the element of arc length that we revolve, take the piece, revolve it about a given axis. Revolution about x-axis. So again, the distance to the x-axis will be given by the y-coordinate. So just remember, we have, in this case, r of t equals x of t, y of t, and we'll just say that our interval is like what I used before, alpha to beta, whatever you want to use, whatever letters, it doesn't matter. So we'll get surface area will just be 2 pi. Remember, we had the 2 pi from our understanding of the surface area of a frustum. So we have alpha, beta, and then we have And again, what I can do, let me go ahead and sneak in. Let me go ahead and sneak in the distance to the x-axis, which will be y of t. And then we have x prime of t, quantity squared, plus y prime of t, quantity squared, to the 1/2 dt. So remember, with the surface area, we have the concomitant factor of 2 pi from the area of a frustum, and then of course the distance to the axis of revolution. Now 2 revolution about y-axis. So we don't have to start over. Revolution about y-axis. Thinking again using the parametric representation. So S in this case will be 2 pi alpha to beta. Distance to the y-axis will give us the x-coordinate of the parameterization. And then, of course, we have x prime of t, quantity squared, plus y prime of t, quantity squared, to the 1/2 dt. Now, there's a neat problem in your WebAssign that I'll do next class, but here's a quick one. This one is fairly quick. So say we have a circle. So we've got 5, here we go with the thetas, cosine theta, 5 sine theta. And we're just going to look at part of it. Theta runs from 0 to pi over 2. And you're thinking, well, the surface will be a segment of a sphere. We like those. So we want to revolve about y-axis. So now x prime, and I'll just say compute area of surface. So we say x prime will be what? -5 sine theta. This is a nice straightforward example, not as computationally demanding as the last one. And then we have 5 cosine theta, which implies x prime squared plus y prime squared. That'll give us a 25 in both. So that'll be a 25 times sine squared theta plus cosine squared theta. You square both of them, they both have a 25. So that just gives us 25. And so now this implies that the area of the surface will now be 2 pi. And then we have the interval. In this case, this is given to us 0 to pi over 2. So just think about this particular circle. It makes perfect sense. This is kind of neat. You don't get the full sphere, but you get a portion of it. So now we have the distance to the x-axis, which is just the x-coordinate of the, the distance to the y-axis is just the x-coordinate of the parameterization. So this will be 5 cosine theta times the element of arc length. So that will be the square root, oh, how nice, 25 d theta. I don't think I've written a dt anywhere. That's amazing, very amazing. So again, this is a 5 and a 5. So we get 2 pi times 25, 0 to pi over 2, cosine theta, d theta. So this gives us 50 pi. And of course, the antiderivative of cosine is sine. We like these simple integrals you can do in your sleep. So of course, we get 50 pi. And this will be sine, reminds us of our evaluations earlier in the lecture, minus sine of 0. Of course, that's 1, so we get 50 pi, which is not at all a surprise. So the key here, again, if you think about this example, the next idea is to say, okay, well, if we can do arc length, we can now amend the arc length with distance to the axis of revolution with the factor of 2 pi that we get from the area of a frustum. And so now, again, we find that when you put on this additional, add this additional factor, the calculus usually simplifies greatly because it just creates simplicity for like a basic substitution as opposed to a more elaborate one that we had to do with the previous example. But that's fine. That's what you do in calculus. That's just the par for the course, so to speak. But for the next lecture, there's a WebAssign problem where you basically remove a a cone from a sphere. And the way it's stated is really interesting. You just remove it. And then the question is, well, how much of the surface area did you remove? And it really is not, it sounds much more difficult than it is, but I want to go over it just to give you a way to use this new formula. It's actually quite straightforward as long as you think about it, and drawing a little picture like with this circle will help. The idea is that the problem is related to the problem I just did here, but I found even in previous semesters when I would do this, or I lacking doing it, always cause some issues and all. So we'll talk about that, and then we'll do some review examples. Again, just remember that the next topic, Pass the Test, will cover our introduction to polar coordinates. So polar coordinates will be something you may have seen before, but that'll be another way of describing curves, utilizing, taking the Cartesian and transforming it, and of course, starting with polar and transforming it to Cartesian. So this introduction here has given us the calculus of parametric representations. So we'll take this calculus and apply it to polar coordinates. So I think you'll find that interesting. And I know this is such a huge departure from what we've been doing. We've been doing the infinite series, the power series, intervals of convergence, binomial theorem, things like that, kind of really very disparate compared to this. So when we talk about the polar coordinates, I think you'll enjoy that. But as you have time, look back through this, just review these concepts, thinking about the calculus, how we basically go to the parametric representation and extract the Cartesian derivative. It's really an interesting argument. And of course, my arguments are a little bit different from what you'll see in the textbook. That's fine. It's just the way I see it because I've had a lot of background in topology and differential geometry. That's again, just remember, less notation is more. You think when we did this example here, we only use the notation that we had to use. That's it. If we need a variable, it's useful to use the substitution here. That's good. That's good mathematics. But just extra variables because we don't have anything better to do is no good. We don't want to just cover the paper with all kinds of stuff and we don't even know what's going on. So I hope you've enjoyed this. It's fun to teach. And again, it's like we do pre-calculus all over again. Well, if you thought we did a lot of pre-cal this time, when we get to polar coordinates, it'll be pre-cal again. So the beautiful part about the end of Cal 2 is that it gives you an infusion of trig that will help you eventually in Cal 3. And I remember the operative word is eventually, because the multiple integration is towards the end of the course and you're thinking, oh man, I could have used this. But when you get to spherical coordinates and cylindrical coordinates and stuff early on, you'll use a lot of trigs. So this will actually help you. So enjoy your day. I will have my conference hours today. I'll send out invitations, and I wish you well as you continue to work hard and prepare. It will be over soon, so just remember that semesters are finite. You all have a great day, and thanks again for your attendance.